On a clear winter night on the high Antarctic plateau, a satellite once read the surface of the ice at minus 98 degrees Celsius, cold enough to freeze a breath before it leaves the chest. It is the lowest temperature ever recorded on Earth, and by the standards of the universe, it is almost mild. By the end of this video, you will understand how cold the universe truly becomes once you leave this planet, and where the coldest places we have ever found really are. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them. To make sense of that number, and of every colder one that follows it, we have to begin by correcting the way almost all of us picture cold. Cold feels like a presence. It feels like something that arrives, a force pressing at the window, climbing the arms, sliding under a door you would rather keep shut. We talk about letting the cold in, about the cold getting into our bones, as though it were a substance with a will of its own, seeping through the walls from somewhere outside. It is one of the most natural mistakes the human body makes, and almost everything about the real cold of the universe stays hidden as long as we keep making it. Because cold is not a thing. There is nothing there to come in. Cold is what is left when something else leaves, and that something else is motion. Reach into any object around you, the wall, the air, the surface you are resting on, and at a scale far too small to see, none of it is still. It is built from atoms and molecules, and every one of them is moving. In a solid, they quiver in place, straining against their neighbors. In a liquid, they slide and tumble over one another. In a gas, they fly apart, crossing the empty space between collisions thousands of times a second. This motion never entirely stops, and it is not incidental to matter. It is the heat. What we call temperature is simply a measure of how vigorously, on average, the particles in something are moving. A warm object is one whose atoms are jostling quickly. A cool one is filled with atoms that have slowed. Temperature is the speed of the small, invisible crowd inside everything. Once you see it that way, the sensation of cold turns inside out. When you step outside on a winter morning and the air bites at your skin, nothing is flowing into you. The truth is the reverse. Your skin is warm, its molecules are moving fast, and the air around it is moving more slowly, and where the two meet, the fast hand off their motion to the slow. Energy drains out of you and into the air, collision by collision, and the feeling of that draining is the feeling we call cold. Cold is not an arrival, it is a departure. It is the sensation of your own warmth leaving. This is why the same air can feel mild or brutal, depending only on how quickly it pulls your heat away. Still air robs you slowly and feels gentle. Moving air or water carries heat off far faster and feels savage at the very same temperature. The cold itself has not changed. Only the rate of your own loss has. So the Antarctic ice at minus 98 degrees is not a place flooded with some special cold substance. It is matter whose particles have very nearly run down, whose atoms are barely shuffling compared with the frantic motion in your own warm hand. And the reason it could fall that far is precisely that there was almost nothing left to keep it warm. No nearby sea, no thick blanket of moist air, no sun for months, nothing handing motion back to the ice as fast as the ice gave it away. Left alone, with its warmth radiating off into a clear black sky and nothing returning, the surface simply kept slowing, night after night, until it reached a stillness that no other patch of ground on the planet has matched. That single shift, from cold as a substance to cold as the absence of motion, is the key that opens the whole of this journey. Because it tells us which way the universe naturally tends. Warmth requires a source. It requires something actively pumping motion into matter. A star burning, a planet's interior churning, a body like yours turning food into heat. Take the source away, and the motion always leaks outward, always spreads, always thins. Warmth is something that has to be maintained. Cold is what happens on its own, And the moment you grasp that, the proportions of the universe rearrange themselves. We grow up treating warmth as the ordinary condition and cold as the exception, the cold snap, the cold spell, the unusual night. But that is only because we live pressed against a star, inside a thin and unusually cozy shell of air, on one of the rarest kinds of surface there is. Pull back far enough and the picture reverses entirely. The stars are real but scattered, tiny islands of furious motion separated by enormous gulfs. The warm worlds are fewer still. Almost everything else, the vast spaces between the stars, the surfaces of distant worlds, the dark between the galaxies, sits far down toward stillness. Across the universe as a whole, warmth is the strange local accident. Cold is the rule. For nearly the whole of human history, none of this could be known, because cold could only be felt. It was a sensation and a boundary, marked by the moment water stiffened into ice, by breath turning visible in the air, by the ache that crept into fingers left out too long. People knew cold the way they knew hunger or fatigue, from the inside, as something the body reported. They could rank one day against another, this winter against the last, but they had no way to put a number on it, and no reason to suspect how far the scale ran beneath them. The coldest thing most people would ever touch was ice, and ice felt like the bottom of the world. It was not. The discovery that cold could be measured rather than merely suffered, that it could be turned from a feeling into a quantity, compared and recorded and pushed into ranges no human had ever felt, is one of the quiet revolutions in the history of science. And it is the thread we will follow outward. Every figure in this story, from the ice of Antarctica to the surface of a frozen moon to the deepest hollow of empty space, exists because someone learned to read the motion of matter from the outside and write it down as a number. The instruments changed. The principle never did. Cold has always been the same simple thing. The running down of motion, the fading of energy, the slow approach of stillness. Which leaves one obvious question, the one that has to be answered before any journey outward can begin. If cold is motion draining away, and the universe everywhere tends toward less of it, then how far down can it go? Does the motion simply keep thinning forever, growing fainter without limit? Or is there a floor somewhere beneath us, a final stillness past which nothing can fall? The answer turns out to be one of the most exact and most unyielding facts in all of physics, and everything we are about to encounter sits a measured distance above it. The answer is yes. There is a floor. Cold does not thin away forever. It runs down toward a single, exact temperature and can go no lower. And the story of how we found that out without ever reaching it is stranger than the floor itself. The first clue came not from making things cold, but from watching how matter responds as it warms and cools. By the early 18th century, a handful of experimenters had noticed something suggestive about gases. Seal a fixed amount of air in a vessel and warm it, and its pressure climbs. Cool it, and the pressure falls, and it falls in a remarkably orderly way, dropping by a steady, predictable amount for every degree of cooling. The French physicist Guillaume Amonton was among the first to follow that line of reasoning to its unsettling conclusion. If the pressure of a gas keeps falling as it cools, in a straight and even descent, then somewhere far below any cold he could produce in his laboratory, the line must reach the bottom. There must be a temperature at which the pressure would fall all the way to nothing, at which, in some sense he could not yet explain, the gas would have nothing left to give. He could not reach that temperature. Nobody could. It lay hundreds of degrees below anything achievable at the time. But he did not need to reach it to find it. He only had to extend the line. Take the orderly fall of pressure with temperature. Draw it out past the cold you can actually make, and see where it crosses zero. More than a century later, with far better measurements, That crossing point was pinned down with precision, and it always landed in the same place, no matter which gas was used. A little under minus 273 degrees Celsius, minus 273.15 to be exact. Every gas, cooled along its own descending line, pointed to the same floor. In the 1840s, the Scottish physicist William Thomson, later Lord Kelvin, grasped what that shared crossing point really meant. It was not a quirk of gases. It was the bottom of temperature itself. Below it, there was simply nothing. No lower rung, no colder state for matter to occupy. And so he proposed measuring temperature from there, from the true bottom, rather than from the freezing point of water, which is an accident of one particular substance on one particular world. On his scale, 0 is the floor, absolute 0, and the divisions are the same size as the degrees we already knew, so that water freezes not at 0, but at about 273 above it. This is the scale that scientists have used ever since to talk about the cold of the universe, measured in units now called Kelvin. Absolute 0 is 0 Kelvin. The Antarctic record we began with, minus 98 degrees Celsius, sits at about 175 Kelvin, already most of the way down from the warmth of a summer afternoon, and still, as we will see, an enormous distance above the bottom. What does it actually mean to reach that bottom? If temperature is the motion of particles, then absolute 0 ought to be the point where the motion stops, where the quivering, sliding, flying matter inside, everything finally goes still. That is very nearly the right picture, and for a long time it was the whole picture. Absolute 0 was imagined as perfect stillness, the great freeze at the end of the thermometer, a state in which every atom has surrendered its last scrap of motion and simply waits, frozen and silent and exact. But nature, it turns out, does not permit perfect stillness. And the reason is one of the deepest rules in physics. The first barrier is practical, though it is absolute in its own way. It is built into the very business of cooling. To cool something, you must carry its heat away into somewhere colder. That is the only direction heat ever flows on its own, from the warmer to the cooler, never the reverse. But as an object approaches absolute 0, finding somewhere colder to dump its remaining heat becomes harder and harder, because there is almost nothing colder left. Each step you take removes only a fraction of the motion that remains, and the next step removes a fraction of that, and the fractions never quite reach 0. You can have the distance to the floor, and have it again and again, forever, and never arrive. Drawn out into a law, the third law of thermodynamics, it says exactly this. Absolute 0 can be approached as closely as you have the patience and ingenuity to manage, but it can never, even in principle, be reached. It is not a destination. It is a limit, a direction, a point that the universe leans toward without ever touching. And even if you could somehow get there, a second and stranger barrier would still forbid the perfect stillness we imagine. It comes from quantum mechanics, and it means that absolute 0, even reached, would not be silent. The rule is this: at the smallest scales, a particle can never have both a perfectly fixed position and a perfectly fixed motion at the same time. The more precisely one is pinned down, the more unavoidably the other blurs. A particle that had truly stopped, sitting at an exact place with exactly 0 motion, would violate that rule outright. It would be too well defined in both respects at once. Nature closes off that possibility by refusing to let the motion ever fall all the way to nothing. Even at the very bottom of the temperature scale, every particle retains a faint, irreducible tremor, a residual quiver that cannot be removed by any amount of cooling, because it is not really heat at all. It is called zero-point motion, and it is the floor beneath the floor, the last unfreezable shimmer of matter that persists even when every trace of warmth has been stripped away. So the picture of absolute 0 as a great and final stillness is not quite true. It is a stillness with a permanent shimmer running through it, the quietest that matter is allowed to be, but never entirely quiet. That single fact will return near the end of this journey when we come to the coldest places that have ever existed, because it turns out that the closer you press matter toward this forbidden floor, the stranger it begins to behave. At the edge of absolute stillness, ordinary substances stop behaving like themselves and start doing things that have no equivalent in the warm world we live in. The floor is not just a number, it is a doorway. There is something almost defiant in that last refusal of nature to be stilled. Zero-point motion is not a technicality or a rounding error. It is real, measurable energy that remains in matter when everything else has been stripped away, and it has consequences you can detect. It is part of why the lightest substances will not freeze at all near the bottom of the scale, kept liquid by their own irreducible quiver. It sets a hard limit on how perfectly still anything can ever be made, anywhere, by anyone. And it means the bottom of the temperature scale is not a dead, frozen silence, but a kind of permanent, minimal hum, the universe's quietest possible state, which is still not quite quiet. The closer you press toward absolute zero, the more this faint surviving motion comes to dominate, until at the very limit, it is all that is left. Not the stillness we imagined, but the last whisper nature will never allow to fade. For now, what matters is the measuring stick we have built. We have a true bottom, fixed and universal, the same for every substance everywhere in the cosmos. We have a scale that counts upward from it. And we have the realization that everything we ever experience, every fire, every summer, every living body, the searing surface of the sun itself, sits crowded into the warm end of that scale, while the universe at large lies far down toward the cold end, a measured distance above a floor it can approach but never reach. There is only one thing still missing, and without it, none of the numbers in this story could exist. We have a scale. We do not yet have a way to read it at a distance. It is one thing to measure the temperature of a gas sealed in a laboratory vessel with an instrument resting in the gas itself. It is another thing entirely to know the temperature of a crater on the moon, or the surface of a world billions of kilometers away, or a wisp of gas drifting between the stars, places no instrument will ever touch, places no human will ever stand. And yet we do know those temperatures, often to within a few degrees. The question of how is the next step in the journey, and the answer is hidden in the light. The answer is that warmth announces itself. Everything in the universe that has any temperature at all, anything standing even slightly above absolute zero, gives off light. Not necessarily light you can see, but light all the same. A steady outpouring of electromagnetic radiation, streaming away in every direction, simply as a consequence of being warm. It happens for the same reason heat exists in the first place. The particles inside matter are moving, and many of them carry electric charge, and a moving charge cannot help but radiate. So every warm thing glows. Your body glows. The walls around you glow. The ice of Antarctica glows. The faintest, coldest wisp of gas between the stars glows. The only thing that would not glow is a thing at absolute zero itself, and we have already seen that nothing is ever quite allowed to get there. This is the loophole that makes the whole of this journey possible, because it means a thing does not have to be touched to be measured. It is broadcasting its temperature continuously, written into the light it emits. And if you can catch that light and read it, you can know how warm or cold the object is from across a room, or across the solar system, without ever going near it. The trick is that the light carries the temperature in a very specific way. It is not just that hotter things glow more brightly, though they do. It is that the color of the glow shifts as the temperature changes, and it shifts according to an exact and universal rule. You can watch it happen in something as ordinary as an iron poker pushed into a fire. Cold, the poker emits light too faint and too long in wavelength for the eye to catch. It is glowing. But in the infrared, below the red end of what we can see, warm it, and the glow climbs into the visible. First a dull red, then a brighter orange, then yellow, and finally, if it grows hot enough, a brilliant blue-white. The poker is keeping no secrets. Its color is reporting its temperature, rising step by step up the spectrum as it heats. Near the end of the 19th century, the physicist Max Planck worked out the precise law behind that shifting glow. The exact relationship between an object's temperature and the spread of light it pours out at every wavelength. The details are intricate, but the consequence is wonderfully simple to use. Catch the radiation coming off something, measure how it is distributed across the wavelengths, and the shape of that distribution names the temperature. There is no ambiguity. A surface at 1,000 degrees has a glow of one particular character. A surface at 50 degrees above absolute zero has a glow of quite another, and the two cannot be confused. Read the light, and you read the temperature. Scientists call the figure you get this way a brightness temperature, and almost every cold number in this story, the craters, the moons, the distant worlds, is a brightness temperature, inferred from radiation rather than measured by contact. The catch for cold things is that their glow falls far outside the range our eyes evolved to see. A warm poker eventually reaches into the visible, but cold objects never do. The colder a thing is, the longer the wavelength of the light it gives off, and the fainter that light becomes, sliding deeper into the infrared and, for the very coldest, all the way down into microwaves. The Antarctic ice does not visibly shine. It glows in the far infrared, in wavelengths no human has ever seen, with a faint thermal light that pours steadily up into the sky. A satellite passing overhead, carrying an instrument tuned to exactly those wavelengths, gathers that light and reads from it a surface temperature, and that is how we know the plateau reached -98 degrees on a night when no person was anywhere near it. No thermometer was placed on the ice. The ice told the satellite itself, in infrared, and the satellite wrote it down. The same method reaches as far as we need it to go. A frozen moon radiates faintly in the infrared, and a passing spacecraft reads its surface temperature from the glow. A cold cloud of dust between the stars radiates in the infrared and microwave, and a telescope tuned to those long wavelengths maps how cold it is, pocket by pocket, though no probe will ever travel there. Every figure we are about to encounter, however remote, however unreachable, was obtained this way, by catching light that began as the motion of distant matter and ended in a detector built to translate it back into a temperature. The instruments differ enormously. A sensor cooled and shielded aboard an orbiting observatory has little in common with a glass tube of liquid, except the one thing that matters. Both are reading the same underlying quantity, the motion of particles, the warmth or its absence. There is an unexpected gentleness to measuring this way. To read a temperature from the light a thing emits is to take nothing from it and add nothing to it. The object is not touched, not warmed by the contact of an instrument, not disturbed in any way. It goes on radiating exactly as it would have, indifferent to being watched. A crater that has sat in darkness for 1 billion years is not changed by the spacecraft that finally measures it. The measurement simply notices what was always being broadcast. Across the whole of this journey, the coldest places will be observed without ever being intruded upon. Their stillness intact, their temperatures gathered from a respectful distance out of the light they cannot help but give off. And there is one last consequence, easy to miss, that will matter enormously before we are done. If everything with a temperature glows, then catching that glow tells you not only how cold a thing is, but that it has a temperature to read at all. Point a sensitive enough instrument at what looks like utterly empty space, no star, no world, no cloud, just the dark between things, and you might expect to catch nothing whatsoever. but you do not catch nothing. Even the emptiest dark is glowing faintly, with a whisper of radiation that has its own exact temperature, the same in every direction you look. Empty space, it turns out, is not at absolute zero either. It has a temperature of its own, and finding out what sets it is one of the destinations still ahead. First, though, we have the tools we need to go back to where we began and read the real records properly, to return to the coldest ground on Earth and ask not just how cold it gets, but why this one frozen continent, out of the whole surface of the planet, is able to fall further than anywhere else. We left the plateau as a single startling number. Now we can ask what stands behind it, why this one place, out of the entire surface of the Earth, sinks lower than anywhere else, and how we know just how far. For most of the 20th century, the record belonged to a ground instrument at a remote Soviet outpost called Vostok Station, set deep in the interior of East Antarctica, almost as far from any coast as it is possible to get on the continent. The station sits high, more than 3,500 meters above sea level, not because it stands on a mountain, but because it rests on top of the Antarctic ice sheet, which is itself kilometers thick. On the 21st of July, 1983, in the depths of the southern winter, the instruments there read minus 89.2 degrees Celsius. It was the lowest temperature ever directly measured by a thermometer at the surface of the Earth, and it stood unbeaten for 30 years. Then, in the second decade of this century, scientists combing through years of satellite data found something colder still, not by sending anyone into the dark, but by reading the infrared glow of the ice from orbit. Sifting the records of instruments aboard spacecraft such as Landsat 8, along with the long archive of the MODIS sensors, they mapped the surface temperature of the entire plateau across many winters, and in the very highest stretches, they found pockets that had fallen to around minus 98 degrees Celsius. Later, more careful analysis settled the very coldest confirmed reading at about minus 94.7. These were not the air temperatures a weather station measures a meter or two above the ground. They were skin temperatures, the temperature of the ice surface itself, caught in tiny hollows on the clearest, stillest nights of the year. But they pushed the floor of Earth's cold several degrees lower than any thermometer had ever recorded, and they were gathered from hundreds of kilometers overhead from places no person has stood. What is it about this particular patch of the world that lets it fall so far? Not a single cause, but a rare alignment of several, each one stripping away a different source of warmth until almost nothing is left to keep the surface from running down. It begins with height. The plateau is one of the highest large surfaces on the planet, lifted by the thickness of the ice into thin, frigid air. The higher you go, the less atmosphere lies above you, and the less there is overhead to absorb the surface's escaping heat and radiate part of it back down. Up here, the warmth that leaves the ice mostly keeps going, straight out toward space. Then there is dryness. The air over the high interior is among the driest on Earth, so cold that it can hold almost no water vapor at all. This matters more than it might seem, because water vapor is the main reason any surface stays warm at night. It is the gas that catches the infrared glow rising off the ground and sends a share of it back down, the invisible blanket that keeps most of the world from freezing hard after dark. Over the plateau, that blanket is nearly gone. The ice glows its heat upward, and with so little vapor to intercept it, the warmth escapes almost unimpeded into the sky. Then there is darkness. For months on end, through the polar winter, the sun never rises. No sunlight arrives to replace the heat the surface is steadily losing. The ice radiates and gets nothing back from above, day after day that are not really days at all, and the temperature sinks lower with each one. And then, holding it all together, there is stillness. The very coldest readings never come during storms. They come on the calmest, clearest nights. When there are no clouds, clouds would act like the missing water vapor, trapping warmth, and, above all, when there is no wind. Wind is warmth's ally, because it stirs the air and drags slightly warmer layers down to the surface, interrupting the loss. Let the air go perfectly still under a clear black sky, and nothing interferes. The surface and the empty sky simply exchange radiation, the surface always giving more than it receives, until it has fallen as far as the long night allows. There is one final ingredient, and it is the reason the very lowest readings sit in particular spots rather than spread evenly across the plateau. Cold air is dense and heavy, and like water it flows downhill and gathers in low places. On the broad high surface of the ice, there are shallow dips and hollows, barely perceptible depressions, and on a still clear night, the coldest air drains gently into them and pools there, sitting trapped while it goes on, radiating away its last warmth. The -98 pockets were found in exactly such hollows, along the highest ridge of the plateau between two great domes of ice, known as Dome Argus and Dome Fuji, the coldest air, settling into the coldest hollows. On the coldest nights, in the coldest part of the continent. Notice what is absent from that whole account. There is no violence in it anywhere. The deepest cold on Earth is not produced by blizzards or by some dramatic plunge. It is produced by calm, by clear skies, still air, and the simple, patient leaking away of heat when nothing is there to replace it. This is the same lesson the first record hinted at, now made concrete. Extreme cold is not an event that happens to a place. It is what a place settles into when it is finally left undisturbed, when every source of warmth has been removed or shut off, and the matter is allowed to run quietly down towards stillness. The coldest ground on the planet is also the most peaceful. It is worth being precise about what those two records are, because they measure slightly different things. The Vostok figure, -89, is an air temperature, the reading of a thermometer in a louvered screen a meter or two above the snow, the standard the world's weather records are kept in, which is why it remains the official coldest air temperature ever measured on Earth. The satellite figures, the -94 and the -98, are skin temperatures, the temperature of the surface of the ice itself, which on a clear, calm night can run several degrees colder still than the air just above it, because the ground radiates its heat away fastest of all, and the air takes time to catch up. Both are real. They simply read the cold at two different heights. Together, they bracket the true floor of the planet's surface, an air record set by an instrument on the ground, a surface record set by an instrument in orbit, the two of them agreeing that nowhere else on Earth comes close. For the small crews who keep the interior stations running, that peace is the texture of daily life through the winter. Vostok is one of the most isolated inhabited places anywhere on Earth. For much of the year, no aircraft can reach it. The air too thin and too cold for engines and crews alike. And the people there are effectively sealed in with the dark and the cold until the sun returns. They are the ones who, for decades, read the instruments that held the record, living at the bottom of the temperature scale, inside the very stillness the numbers describe. And yet, for all that, the plateau is the floor only of the Earth, not of anything beyond it. The reason it cannot go lower is the same reason the planet remains habitable at all. It is part of a system that will not stop resupplying warmth. The sun always returns in the spring. The atmosphere is always circulating, always nudging heat poleward from the warm middle of the world. Beneath and around the whole frozen continent lies an ocean holding an immense reservoir of heat that the cold can never quite escape. Even the stillest hollow on the highest ridge is only ever borrowing its extreme. The system around it will always, in time, intervene. To find cold that is not held up from below like this, cold with nothing underneath it pushing back, we will have to leave the planet entirely. But before we rise away from the surface, there is a puzzle worth pausing on, because it sharpens everything we have just seen. There is a second great frozen cap at the other end of the world, also locked in months of winter darkness, also buried under ice and snow, and it never comes anywhere close to these temperatures. The Arctic, for all its cold, cannot fall the way the Antarctic plateau falls, and the reason why turns out to reveal exactly what makes that plateau so singular. The puzzle is real. The Arctic is frozen, dark for months, capped with ice and snow, and on the face of it, it has every reason to be as cold as its southern counterpart. Yet in the central Arctic, the deep winter air settles to perhaps -40 or -50 degrees, and stops there, dozens of degrees short of the Antarctic plateau. Two frozen worlds, both buried in polar night, and one of them simply cannot fall the way the other does. The reason is a single difference in what lies beneath the ice, and it explains almost everything. The Antarctic is a continent surrounded by ocean. The Arctic is an ocean surrounded by continents. Invert the geography like that, and you invert the cold. Stand on the Antarctic plateau, and what is under your feet is land, or rather kilometers of ancient ice resting on land, a deep cold solid that holds no warmth in reserve and lifts you high into thin dry air. Stand on the Arctic ice in winter, and what is under your feet is something entirely different. A thin lid of frozen sea, a few meters thick, floating on a whole ocean of liquid water. That ocean is the difference. Seawater cannot get colder than about -2 degrees before it freezes solid, and the vast body of it beneath the ice stays right around that temperature all winter long. By the standards of the plateau, -2 degrees is tropical. And that mild, enormous reservoir sits directly below the surface, leaking its heat upward through the thin ice the entire time, constantly resupplying warmth to the world above. The Arctic surface cannot run down toward real cold, because something underneath it never stops pushing heat back. Everything that made the plateau so extreme is missing here, and missing for the same underlying reason. The plateau was high. The Arctic Ocean is at sea level in denser air. The plateau was bone dry. The ocean breathes water vapor into the Arctic air, and that vapor is exactly the blanket that traps escaping heat and holds the surface warmer through the night. The plateau was cut off from any reservoir of warmth. The Arctic is floating on top of one. The recipe for extreme cold is isolation from every source of heat, height, dryness, darkness, stillness, and above all, distance from any reservoir. And the Arctic fails the most important ingredient. Its reservoir is right there under the lid. There is a second, subtler way the ocean holds the Arctic warmer, and it shows how grudgingly the cold takes hold over water. The skin of sea ice is not a sealed lid, it is a leaky one. Ice conducts heat, and the few meters of it floating on the Arctic Ocean let the warmth of the water beneath seep steadily upward, through the ice and into the air above. The thinner the ice, the more heat escapes, so the ocean is forever fighting the freeze from below, topping up the very surface it is trying to lose. And the cold air that does form behaves in a way that limits how far it can fall. Chilled air is dense, so it settles into a shallow layer pressed against the surface, with slightly warmer air resting on top of it. An inversion, the temperature rising rather than falling as you climb away from the ground, the reverse of the everyday world. That cap of warmer air sits on the cold like a lid, holding it thin and keeping it from deepening without limit. On the high plateau, with kilometers of frozen ice below and no reservoir within reach, none of these rescues exist. The cold there has nothing working against it, and so it falls and falls. In the Arctic, something always pushes back. The exception proves it beautifully. There are a few places in the far north that do approach Antarctic-style cold, and every one of them is a place where the ocean has been shut out. Across the interior of the Greenland ice sheet, high, dry, landlocked ice, a small cousin of the Antarctic plateau, temperatures have fallen below -69 degrees. In the landlocked valleys of northeastern Siberia, around villages such as Oymyakon and Verkhoyansk, far from the moderating sea, the air has dropped past -68, the coldest ever recorded in an inhabited place in the northern hemisphere. These are the northern spots that borrow the southern recipe. Get up high or get far inland, away from the water, onto deep cold land under a clear dry sky, and the cold begins to deepen the way it does at the bottom of the world. Wherever the ocean can reach, it holds the floor far above the true cold. Only where it is banished does the cold come down. This is the same principle we began with, written across the whole planet. Warmth has to be supplied. It always traces back to a source and a reservoir holding energy in place. Cold is simply what is left when the supply is cut. The Antarctic Plateau is the coldest ground on Earth because it is the most thoroughly isolated, lifted high, wrung dry, plunged into months of dark, and ringed away from the great ocean reservoir by distance and by the circling currents of the Southern Ocean. The Arctic, for all its ice, can never achieve that isolation because the reservoir is the very thing it is built on. There is a human shape to this contrast, too. The Arctic, kept mild by the ocean beneath it, has been home to people for thousands of years, communities living on and around the sea ice, drawing life from the water that also keeps the air from ever falling all the way down. The Antarctic interior has no such history and no native life at all. Only small crews who arrive, endure the dark, and leave. The same ocean that prevents the deepest cold is the thing that makes the North livable. Where the cold can truly deepen, life cannot easily follow. Isolation buys you extreme cold and charges life as the price. And that is the thread to carry off the planet, because everything ahead is an exercise in deeper and deeper isolation. Out beyond the Earth, there is no ocean to float on, no reservoir to lean against, no atmosphere circulating warmth poleward, no spring to wait for. The sources of heat grow fewer and more distant until, in the deepest places, there is essentially nothing pushing back at all, and the cold can finally fall the way the plateau only hints at. But we are not quite finished with the Earth. Before we rise away from the surface for good, there is one more cold place that belongs to this planet, and it is stranger than either pole because it is not on the ground at all. The coldest spot the Earth owns is not in Antarctica or the Arctic. It is high overhead, in a layer of our own sky that almost no one ever thinks of, and reaching it means looking not poleward, but straight up. We think of the sky as getting colder the higher you go, and for a while it does. Climb a mountain and the air thins and chills. The peaks wear snow that the valleys never see. Higher still, where the airliners cruise near the top of the layer we call the troposphere, the air outside the window has fallen to around -60 degrees Celsius. This is the familiar pattern, the one our bodies expect. Up is cold, but it does not continue. Keep rising, and the atmosphere does something that overturns the intuition entirely. And hidden in what it does next is the coldest place the Earth possesses, along with the final clue we need before leaving the planet behind. Above the troposphere, the temperature stops falling and begins, strangely, to climb. This is the stratosphere, and it runs warm at the top for a specific reason. It contains the ozone layer, and ozone drinks in the ultraviolet light pouring down from the sun, soaking up that energy and warming the air around it. So there is a warm ceiling some 50 kilometers up, heated from above by sunlight rather than from below by the ground, a layer that gets warmer the higher you go, the exact reverse of the world we know. And then, above that warm ceiling, the pattern flips one final time, and this is where the cold lives. Beyond the stratosphere lies the mesosphere, stretching from around 50 kilometers up to about 85, and here the temperature plunges again, harder than anywhere below. There is no ozone up here to catch the sunlight, and the air has grown so thin that it can hold almost no warmth at all. With nothing to heat it and almost nothing to it, the mesosphere simply gets colder and colder with height, all the way to its upper boundary, a layer called the mesopause, the lid at the top of the mesosphere, around 85 to 100 kilometers above your head. The mesopause is the coldest place in the entire Earth system. Not the Antarctic plateau, not the pole of either hemisphere. This thin, near-empty seam of sky, some 80-odd kilometers straight up. Its temperature averages around minus 90 degrees Celsius, already matching the coldest ground on the planet, and over the poles in summer, it can fall to around minus 100 degrees, dipping toward 130 Kelvin, colder than anywhere a human has ever stood. The lowest naturally occurring temperatures anywhere on or around the Earth are not at the bottom of the world. They are over our heads. And it carries a final oddity, almost a joke at the intuition's expense. The mesopause is coldest not over the winter pole, plunged in darkness, but over the summer one, bathed in unbroken daylight. The circulation of the high atmosphere lifts air over the sunlit summer pole, and as that air rises into the thinning heights, it expands and cools. The same way air escaping a pressurized canister turns frigid, and it cools so effectively that the coldest spot in the planet's whole atmosphere sits above the pole that never sees night. That extreme cold leaves a visible signature, and it is one of the loveliest sights the sky offers. Even at the mesopause, there are faint traces of water vapor and a sprinkling of fine dust, some of it the debris of meteors burning up at exactly these altitudes. Where the air falls cold enough, that vapor freezes onto the dust into crystals of ice, and they gather into the highest clouds on Earth, noctilucent clouds, night-shining clouds, drifting some 80 kilometers up at the edge of space. They appear only in deep twilight, after the sun has set for everyone on the ground, but still reaches up to catch the ice far overhead, and they glow a pale electric blue against the darkening sky. The coldest place the Earth owns is also the birthplace of its highest and strangest clouds, ice made in the one part of the atmosphere cold enough to freeze the last whisper of water out of almost nothing. But it is what lies just above the mesopause that matters most for the journey ahead, because there the atmosphere springs one last paradox, and that paradox is the key that unlocks all the cold of space. Rise past the mesopause into the layer above, the thermosphere, where the International Space Station orbits, and a thermometer's reading would seem to go mad. By the official measure, the temperature there is not cold at all. It is searing, hundreds of degrees, climbing past 1,000 in places, hotter than molten rock. And yet an astronaut floating in that layer would not be scorched. In shadow, they would freeze. How can a place be 1,000 degrees and freezing at the same time? The answer dismantles the everyday idea of temperature, and we need it dismantled before we can go any further. Temperature, properly, measures only one thing: how fast the individual particles are moving. By that measure, the thermosphere genuinely is blazing. The few molecules up there are flying at tremendous speeds, every bit as fast as molecules in something truly hot. But how warm a place actually feels, how much heat it can deliver to your skin, depends on something temperature alone leaves out: how many particles there are to deliver it. And up there are almost none. The air is so unimaginably thin that those ferocious, fast-moving molecules are spread impossibly far apart, and only a handful ever strike you. Each one is hot, but there are far too few of them to carry any meaningful warmth. A thermometer in the thermosphere reads cold, not because the particles are slow, they are not, but because so few of them ever arrive to share their motion. This is the distinction that everything beyond the Earth turns on. Temperature is the speed of the particles. Heat is what they can actually transfer to you, and that depends on having enough of them to matter. Down here at the surface, where the air is dense and the particles are everywhere. The two march together and we never have to tell them apart. Up at the edge of space, where the particles thin almost to nothing, they finally come apart. And the place can be furiously hot by one measure and bitterly cold by the only one your body would care about. Carry that split with us, because we are about to step into a place where the particles thin, not almost to nothing, but very nearly to nothing at all, where the air gives out entirely and the old question, how warm is it here, stops meaning what it used to. Beyond the last traces of atmosphere, temperature is no longer something you read from the air around you, because there is no air around you. From here on, warmth and cold are decided by something else entirely. They are decided by light. We say space is cold, and the words feel obviously true. But they hide a confusion that has to be cleared away. Because space is not cold in the way a winter night is cold, and understanding the difference is the whole secret of every temperature still ahead of us. A winter night is cold because the air around you is cold, because countless chilled molecules are pressed against your skin, carrying your warmth away. That is what cold has meant for the entire journey so far. The slowed motion of the matter touching you. But space is very nearly empty. Across vast stretches of it, there is so little matter that the idea of the temperature of the air simply has nothing to attach to. There is no air, no crowd of particles touching anything, no medium to be warm or cold at all. You cannot take the temperature of empty space the way you take the temperature of a room, because emptiness has almost nothing to measure. Space is not a cold substance surrounding you. It is the absence of any substance to begin with. So what decides whether an object out there is warm or cold? With no air to touch it, only one thing can reach it across the emptiness, and only one thing can leave it: light. Radiation. An object in space warms by absorbing the light that falls on it, overwhelmingly, sunlight, and cools by giving off its own thermal glow, the radiation that everything warm emits. It has no other options. It cannot be warmed by contact, because nothing is touching it. And it cannot be warmed by a circulating fluid, because there is no fluid. It hangs in the dark, taking in whatever light arrives and radiating its own light away, and it settles at exactly the temperature where those two flows balance. Cold and warmth in space are not about the surroundings. They are about the books, what comes in as light against what goes out as light. This is why the same object in space can be scorching and freezing at the same moment. Turn a surface toward the sun, and it drinks in that flood of light with nothing to carry the heat away, no breeze, no air to spread it, and it climbs past the boiling point of water, over 100 degrees, baking in the raw sunlight. Turn the very same surface into shadow, cut it off from the sun, and now it only emits. It pours its warmth out into the dark and gets nothing back, and it plunges toward deep cold. The International Space Station lives this contrast on every orbit. Its sunlit face heats to around plus 120 degrees Celsius, while its shadowed face falls to around minus 150, the two extremes separated by nothing more than which way the surface happens to point. The station and the suits the astronauts wear must be built to survive both at once, one side of a spacewalker roasting, the other freezing, on the same body in the same instant. The reason these extremes can sit side by side and persist is that in a vacuum, heat has almost no way to move. On Earth, heat travels by three routes: by direct contact, spreading through whatever it touches; by the churning of fluids like air and water, carrying warmth from place to place; and by radiation as light. Take away the air and the first two routes vanish. Nothing is in contact, nothing is flowing. Only radiation is left, and radiation moves heat slowly. This is precisely the principle of a vacuum flask, the thermos that keeps coffee hot for hours. Its secret is a gap of vacuum sealed inside the walls, and that empty gap blocks contact and blocks the flow of any fluid. leaving only the feeble trickle of radiation to carry heat across. Space is the ultimate thermos. A sunlit surface and a shadowed one, a hand's width apart, can differ by hundreds of degrees and simply stay that way, because almost nothing is able to carry heat from one to the other. This is why building anything that must survive in space is, to a surprising degree, a problem of managing temperature and of managing the one thing that moves it. A spacecraft has no air around it to even out the warmth, so its sunlit and shadowed sides pull apart in temperature, and every probe must be wrapped and plumbed to hold itself together against that pull. The crinkled gold and silver foil that gives so many spacecraft, their strange appearance is exactly this defense. Layer upon layer of thin reflective film, a blanket built to do what the vacuum flask does, throttling the trickle of radiation so the warm parts stay warm and the cold parts cannot drain them. Heat is shuffled deliberately from the sunlit side to the dark side through pipes and radiators, and an instrument that must run cold is aimed away from the sun out into the black so it can pour its own warmth into empty space and chill itself by sheer exposure. The same vacuum that makes space such a brutal place to control temperature is also the tool the engineers reach for. Surround something with emptiness, and you can decide almost entirely by how you turn it toward the light or away from it, whether it bakes or freezes. In a place with no air, keeping a machine alive means choreographing, watt by watt, the only flow of heat there is. Once you see space this way, the rest of the journey rewrites itself. Out here, cold is no longer made by frozen ground or chilled air, because there is neither. Cold is made by light, or rather by its absence, and there are only two ways to be starved of it. The first is distance. Light spreads and thins as it travels outward from a star, so the farther a thing drifts from every source of light, the less warmth reaches it, and the colder it settles. The second is shadow. Hide from the light altogether, tuck into a place that starlight cannot reach, and you receive nothing at all. Every colder place we are about to visit owes its cold to one of these, or to both, to being far from the fires or hidden from them. It is the deepest form of the same rule we have followed the whole way. On the Antarctic plateau, cold came from isolation, from being cut off from every reservoir of warmth the Earth could offer. In space, the isolation becomes total and the reservoir becomes light itself. To be cold, out here, is simply to be cut off from the light, by distance or by darkness, with nothing else to lean on. And yet there is a limit even to this, a subtlety that will become one of the journey's destinations. You might think an object drifting in perfect shadow, infinitely far from every star, would just keep cooling forever, radiating its warmth away until it reached the absolute floor itself. It does not. No matter how far you go or how deep into shadow you hide, a faint light still finds you, a whisper of radiation coming from no star in particular, falling on everything from every direction at once, the same faint glow everywhere in the universe. It is not much, but it is enough to stop the cooling at a definite temperature, a floor set not by any nearby fire, but by the universe as a whole. What that glow is, and why it sets the temperature of empty space, is one of the strangest answers still waiting for us. First, though, we can watch all of this, the rule of light, the brutal split between sun and shadow, the deep cold of places the light cannot reach, written starkly on a world close enough to see in detail. It has no air to blur the contrasts, no weather to soften them, and in certain hollows near its poles, it hides shadows that have not been touched by sunlight in billions of years. It is the nearest place where cold is made purely by darkness, and it is the first true cold trap on our way out. The moon. The moon writes the rule of light in its starkest possible form, because it has no atmosphere to soften anything. There is no air to spread warmth from the sunlit side to the dark, no blanket of vapor to hold heat through the night, no weather to blur the line between light and shadow. There is only bare rock and dust, the sun, and the geometry of where the light happens to fall. Where sunlight lands, the ground bakes. Where it does not, the cold comes down with nothing to stop it. The same world, at the same moment, holds both. Begin with its ordinary day and night, which are already extreme. The moon turns slowly, so slowly that a single day-night cycle takes about a month. Roughly 14 Earth days of unbroken sunlight, then roughly 14 of unbroken dark. Through the long lunar day, the sunlit ground absorbs the sun's full force, with no air to carry the heat away, and the surface climbs to roughly 120 degrees above zero, hot enough to boil water away in an instant. Then the sun sets, and for 2 weeks there is nothing. No air holds the warmth. The ground simply radiates its heat into the black sky and gets nothing back, and the temperature falls and keeps falling, down past -150, toward -170. A swing of nearly 300 degrees between noon and midnight, on a world close enough to see with the naked eye, driven by nothing but the presence or absence of light. But the long night is not where the moon hides its deepest cold. For that, you have to find a place where the day never comes at all, and the moon has them. The trick is in the tilt. The Earth leans over at 23 degrees, which is why we have strong seasons and why the sun climbs high overhead in summer. The moon barely leans at all. Its axis is tipped only about 1.5 degrees. That means at the lunar poles, the sun never rises more than a hand's breadth above the horizon. It crawls around the edge of the sky, low and grazing, and never climbs. And wherever the polar landscape dips into a deep crater, the crater's own walls block that low, grazing sun completely. Down on the floor of such a crater, sunlight has not fallen, not at midday, not in any season, not once. These are the permanently shadowed regions, and some of them have lain in unbroken darkness for billions of years, since close to the birth of the moon itself. In those frozen pits, there is no day to interrupt the cold. The floor only ever loses heat, radiating slowly into space with nothing to resupply it, century upon century, eon upon eon. We know how far it falls because we have read these craters from orbit, in infrared, exactly the way we read the Antarctic ice, catching the faint thermal glow of surfaces no craft has touched. NASA's Lunar Reconnaissance Orbiter, carrying an instrument named Diviner, mapped the temperatures of the polar shadows, and in the coldest of them, in craters such as Hermite near the North Pole, and in hollows near the south, it found surfaces sitting at around 25 to 30 Kelvin. That is roughly -245 degrees Celsius. It is among the coldest temperatures ever measured anywhere in the entire solar system. Colder, as we will see, than the distant surface of Pluto, far out beyond the planets. And it is here, on the moon, the nearest world to our own. These shadows do more than merely sit cold, they hoard. A place that cold, that still, and that permanent becomes a trap from which nothing volatile can escape. Across the long history of the solar system, water and frozen gases are forever being delivered to the inner worlds, carried in by comets and asteroids, forged in slow reactions on the surface, drifting as stray molecules across the moon. Most of it, landing on sunlit ground, is warmed and lost back to space. But any of it that happens to wander into one of these permanently shadowed craters and freeze onto the floor is locked there for good. There is never any warmth to drive it off again. And so, over billions of years, the cold traps have quietly gathered ice, frozen water, and other volatiles, sealed in the dark. We have confirmed it. In 2009, a mission was deliberately crashed into one of these southern shadows, and the plume it threw up carried the unmistakable signature of water ice, frozen in a crater that has never felt the sun. The deepest cold on the moon is not empty. It is an archive, holding everything that has drifted into it since the worlds were young. It is worth pausing on just how cold those numbers are. 25 Kelvin is colder than the surface of any planet, colder than the most distant moons we have measured, colder than almost anywhere the sun's family reaches, and it is found 250,000 kilometers away, on the world we can see on any clear night with our own eyes. The same moon, whose sunlit rock could boil water, hides, a short walk over its own horizon, pockets colder than the frozen plains of Pluto. Nothing about the moon's distance from the sun explains it. At noon, those very craters would be scorching if any light could reach them. The cold is built entirely out of darkness, out of a shadow so perfectly placed and so long unbroken that warmth simply never arrives, and the floor of the crater has spent the whole history of the solar system doing nothing but slowly letting go of heat it can never get back. It is the purest demonstration anywhere nearby of what happens when the light is removed, not for a night or a season, but for all of time. Hold the strangeness of this in mind. On one small airless world, two places a few kilometers apart, one of them baking at plus 120 degrees through a fortnight of relentless noon, the other locked at minus 245 in a darkness older than the oceans of the earth, colder than a world far out past the orbit of Neptune. They have sat side by side, the searing and the frozen, for the whole age of the solar system, and the only thing that separates their fates is whether the light can reach them. The moon is the rule of light made visible. Warmth where the sun falls, and in the shadows it never reaches. A cold deeper than almost anywhere in the sun's whole domain. For the people who study it, that frozen archive is one of the most valuable things in our neighborhood, a preserved record of what has rained onto the inner solar system across its history. And, for explorers who may one day return to the moon's south pole, a buried store of water sealed in the cold. To read it is to read billions of years held motionless in the dark, undisturbed precisely because nothing warm has ever been allowed to reach it. And the moon teaches the deeper lesson too, that there are two ways to make a place cold, and shadow is the sharper of them. Distance thins the light but never quite shuts it off. A permanent shadow shuts it off completely. The coldest place on the moon is not the farthest from the sun. It is no farther from the sun than we are. It is simply the place the sun can never see. Hidden cold can outdo distant cold, hollow for hollow. But shadow is a local trick, carving out frozen pockets a few kilometers wide, while the sunlit world bakes alongside. To find cold that swallows entire worlds, not hidden hollows but whole surfaces, frozen from one horizon to the other and down to the core, you have to follow the other cold maker. You have to follow distance, outward, away from the sun, to where its light dwindles from a blinding fire to a single bright star among the rest, and warmth becomes something a world can no longer hold on to at all. Shadow was the moon's trick, a local cold, carved into hollows a few kilometers wide while the day baked alongside. Distance works on an altogether grander scale. It does not carve out pockets. It freezes whole worlds at once, surface and sky together. And to watch it take hold, you only have to walk outward from the sun, world by world, and see how quickly its warmth gives out. It gives out faster than intuition expects, because sunlight does not simply fade with distance. It thins in a precise and punishing way. The light leaving the sun has to spread across an ever larger sphere as it travels outward, and the surface of that sphere grows with the square of the distance. So doubling your distance from the sun does not have the light that reaches you, it quarters it. Go 3 times as far and you are left with a 9th. The dimming runs away from you the farther out you go, and with it goes the warmth. The first step out from the Earth already shows the pattern. Mars orbits about 1.5 times as far from the sun as we do, so it receives a little under half our sunlight to begin with, and then it throws away almost all the warmth that light delivers, because its atmosphere is 100 times thinner than ours, far too slight to hold any heat through the night. The result is a world of savage swings. On a summer afternoon at the Martian equator, the ground in full sun can warm to something almost mild, a few degrees above freezing. But the moment the sun goes down, with no blanket of air to hold the day's warmth, the surface plunges, falling by 100 degrees or more before dawn, down past -80. And at the winter poles, through the long polar night, it goes further still, down to around -143 degrees Celsius. That is cold enough to do something almost unimaginable. It is cold enough to freeze the air itself. The Martian atmosphere is mostly carbon dioxide, and at the winter pole the temperature drops below the point where carbon dioxide turns solid, so the air freezes directly out of the sky and falls to the ground as dry ice frost, building seasonal caps of frozen atmosphere that melt back into gas when the sun returns. A whole world that snows its own air onto the ground each winter and breathes it back into the sky each spring. Keep walking outward, and the cold stops swinging and simply deepens. By the time you reach the giant planets, the sun has shrunk and the light has thinned past the point where day and night mean much at all. These worlds have no solid surface to stand on. They are vast balls of gas, so their temperature is red at the cloud tops, where the faint sunlight meets the outermost air. At Jupiter, 5 times farther out than the Earth, and receiving only about 1/25 of our sunlight, the cloud tops sit near -145 degrees Celsius. At Saturn, twice as far again, they fall to around -180. And at the 2 outermost giants, Uranus and Neptune, the cloud tops drop past -200, so far from the sun that the light arriving is a feeble trickle, and the cold is total and permanent, the same in every season, across the whole face of each world. The outermost giants hold one last surprise, and it sharpens the whole lesson about where cold comes from. You would expect Neptune, the farthest of the planets, to be the coldest, and yet the coldest cloud tops of any major planet belong not to Neptune, but to Uranus, the world just inside it, where temperatures fall to about -224 degrees Celsius, around 49 Kelvin. Uranus is closer to the sun than Neptune, and still it is colder, and the reason reveals something we have leaned on the whole way without naming it. Every other giant planet leaks a steady flow of warmth from deep inside itself, leftover heat from its formation, welling up from the interior and helping to hold the cold at bay. Uranus, for reasons still not fully understood, gives off almost no internal heat at all. It is the one large planet living almost entirely on the meager sunlight that reaches it, with no warmth of its own pushing back. And so, despite sitting closer to the sun, it falls colder than its neighbor. Take away even a planet's own buried heat, and the cold comes down further. It is the same rule once more. Cold is what is left wherever a source of warmth is removed, and Uranus has fewer sources than anything else its size. So distance, all on its own, does what shadow could only do in hollows. It freezes entire worlds, from the snowing air of the Martian poles to the 200-degree chill of the outer cloud tops, with no trick of geometry required, only the sun growing too far away to matter. And we have not yet reached the end of the planets. Beyond the giants, where the sun shrinks at last from a small bright disk into a single brilliant star among the rest, lie the worlds where cold stops being a condition and becomes the entire identity, where the ground itself is made of frozen air and the faint distant sun marks time without ever truly warming anything at all. Keep following that curve past the giant planets and the sun's light fails almost entirely. Out where Pluto travels, around 40 times the Earth's distance from the sun, less than a 1600th of the warmth that reaches us ever arrives. From there, the sun is no longer a disk you could not bear to look at. It is a single brilliant star among the others, bright enough to cast a pale light but far too distant to warm anything. Noon on Pluto is dimmer than deep twilight on Earth. With so little warmth arriving, these worlds do not freeze in patches or in seasons. They freeze entirely, surface to core, permanently, and at these temperatures, the very materials of a world change their nature. Substances we know only as gases or thin air become solid ground. It is cold enough out here that nitrogen freezes, that methane freezes, that carbon monoxide freezes, and these frozen gases form actual landscape, plains and ridges and slow glaciers made of ices that could not exist as solids anywhere near the Earth. Meanwhile, water ice, which on our world melts and flows and shatters, is frozen so utterly hard that it behaves like stone. Out here, water ice is the bedrock, mountains of it standing as rigid as granite, while the soft, shifting, geologically active material is the frozen nitrogen creeping across it. The entire identity of these worlds is dictated by cold. Their rock is our air, frozen solid. We know Pluto in such detail because of one of the most patient journeys our species has ever undertaken. A spacecraft named New Horizons left Earth in 2006 and then traveled for 9 years across nearly 5 billion kilometers, crossing the entire breadth of the solar system, to spend a single day sweeping past Pluto in 2015. One close look, after nearly a decade of falling outward, at a world no probe had ever visited. What it found was a surface at about 40 Kelvin, roughly minus 230 degrees Celsius, and a landscape sculpted entirely by cold. At its heart lies a vast plain called Sputnik Planitia, a basin filled with frozen nitrogen. And the nitrogen is not merely sitting there. It is slowly churning and flowing, a glacier of frozen air, its surface broken into great cells where the ice turns over across millions of years. Pluto even has a wisp of an atmosphere, a thin nitrogen haze. And as the little world drifts farther from the sun along its long orbit, that atmosphere grows colder and begins to freeze out of the sky and fall to the ground as frost. Every process on Pluto is the behavior of a substance held at the edge of its existence by cold. And Pluto is not the coldest of these distant worlds. That distinction, among the places we have actually measured up close, belongs to a moon of Neptune called Triton, and its story carries a genuine shock. We have visited Triton only once, when the Voyager 2 spacecraft swept past Neptune in 1989, the single close encounter humanity has ever had with that world. Voyager measured Triton's surface at about 38 Kelvin, close to minus 235 degrees Celsius, among the very coldest surfaces ever directly measured on any substantial body in the solar system. By every expectation, a world that cold should be utterly dead, frozen into perfect stillness, nothing moving, nothing changing. It is not. As Voyager looked, it saw plumes, dark geysers of nitrogen gas erupting from the frozen surface, shooting several kilometers up into the thin sky and trailing off downwind in long dark streaks across the ice. A world at 38 Kelvin, near the floor of everything we had measured, was visibly actively venting. The faint warmth that reaches it is enough, barely, to drive sunlight a little way into the translucent nitrogen ice, warming a hidden layer just enough to build pressure until it bursts free in a frozen fountain. Even here, at the cold edge of the sun's reach, where the star that lights the place is barely more than a point, cold and activity refuse to be opposites. The coldest measured surfaces in the sun's whole family are not frozen into death. They are alive in slow, strange ways, sculpted and stirred by ices we will never see as solids at home. But notice the number that should stop us. Triton sits at 38 Kelvin, Pluto at 40. And the shadowed craters of the moon, right next door to the Earth, fall to 25, colder than either of these worlds at the distant edge of the planets. Distance, for all its reach, cannot match a permanent shadow, because even out at Pluto and Triton, the sun still delivers its faint trickle of warmth, and these worlds still hold a little heat of their own. They are cold beyond anything on Earth, and still they are warmer than the bottom. To find the real floor of natural cold, then, distance alone is not enough either. You have to go where the sun does not merely dwindle, but disappears among the countless other stars, and stops mattering at all, out past the last of the planets, past the reach of any single star's warmth, into the open dark between the stars themselves. And there, in the emptiest place imaginable, with no nearby fire of any kind, you would expect at last to find absolute zero, or something almost touching it. You do not. Even there, in the deep dark between the stars, a faint and perfectly even warmth reaches everything, a temperature that empty space cannot fall below no matter how far it is from any star. Something fills the emptiness with a whisper of heat, the same faint glow we caught a hint of earlier, the light that finds you even in perfect shadow. What it is, where it comes from, and why it sets the floor beneath all the cold in the universe is the next thing to understand. Point a sensitive enough detector at the emptiest patch of sky you can find. No star, no planet, no cloud, just the black gap between everything, and you do not catch nothing. You catch a faint, steady hiss of microwave light, and it carries a temperature. 2.7 Kelvin, under 3 degrees above absolute zero, around minus 270 degrees Celsius. And here is the part that unsettles. It is the same in every direction. Turn the detector anywhere across the whole sky, and the same faint glow comes back. The same temperature to extraordinary precision, falling on everything from all sides at once. The emptiness is not at absolute zero. The emptiness has a temperature of its own, and it is 2.7 degrees above the floor. This glow is the oldest light in the universe, and it is the reason nothing in nature can passively grow colder than this. To understand where it comes from, you have to go back to the beginning. The early universe was not cold and dark. It was hot and dense and blindingly bright. A glowing fog of particles packed so tightly that light could not travel through it without immediately scattering, the way light cannot pass through the inside of the sun. For a few 100,000 years, the whole cosmos was an opaque, searing haze. But it was expanding, and as it expanded, it cooled. And about 380,000 years after the beginning, it cooled past a threshold, down to a few thousand degrees, cool enough for the particles to settle into stable atoms, and all at once the fog cleared. Space became transparent. The light that had been trapped, scattering endlessly inside the haze, was suddenly set free to travel in straight lines, and it has been traveling ever since, for 13.8 billion years, streaming through the growing emptiness of the universe. That ancient light is what the detector catches. It is the afterglow of the universe's fiery birth, the first light ever to travel freely, still arriving from every direction because it began everywhere at once. But it left as a hot glow of a few thousand degrees, and we catch it now at under 3. What cooled it so far is the expansion of the universe itself. As space has stretched over those billions of years, it has stretched the waves of that ancient light along with it, drawing them out longer and longer. And longer wavelength means lower temperature. The light has been pulled out by a factor of more than 1,000, sliding all the way down from a hot orange-white blaze into the faint microwave whisper we detect today. The hottest moment the universe has ever known, stretched across 13 billion years of expansion, has become the coldest thing that fills it. We did not go looking for this. In 1965, 2 radio engineers at Bell Laboratories, Arno Penzias and Robert Wilson, were trying to use a large antenna for an entirely different purpose, and they could not get rid of a persistent faint hiss in their equipment. It came from every direction in the sky. It did not change with the time of day, or the season, or where they pointed the antenna. They checked everything. They even climbed inside and cleaned out the droppings of pigeons that had nested in it, suspecting the mess was the source of the noise. The hiss remained. It remained because it was not a fault in their equipment at all. They had stumbled onto the afterglow of creation, the cold, faint, oldest light in existence, soaking the entire sky, and the accidental discovery of that 2.7-degree glow became one of the strongest pieces of evidence that the universe had a hot beginning. Now hold what this glow actually is, because it reframes everything. It fills all of space, every cubic centimeter of the universe, in every direction, the most widespread and most uniform thing there is. The whole cosmos sits inside this faint bath at 2.7 Kelvin. And that is exactly why empty space cannot fall to absolute zero. Any object adrift in the deepest dark, however far from every star, however perfectly hidden in shadow, is still bathed on all sides by this ancient glow. It cannot radiate itself colder than its own surroundings. As it tries to cool, the background light keeps gently topping it up. So it settles at the temperature of the bath, around 2.7 Kelvin, and there it stops. This is the floor we kept sensing beneath the journey. It is the faint warmth that reaches everything, even in perfect shadow. It is the temperature of the void, and it resets the whole scale of cold we have been climbing down. The Antarctic plateau, at 175 Kelvin, is balmy by this measure. The shadowed craters of the moon, at 25, are still nearly 10 times warmer than the bottom. Triton, Pluto, every frozen world at the edge of the sun's reach, all of them sit far above the temperature of empty space itself. 2.7 Kelvin is the natural floor. Left to itself, with no star to warm it, nothing in the universe drifts colder than the space it floats in. The void is the cold standard against which every other cold is measured. And it is almost perfectly smooth. Wherever you point the detector, the temperature of that ancient glow is the same to within a few parts in 100,000, one of the most uniform things ever measured, a single temperature wrapped around the entire sky. But not exactly the same. There are faint patches, fractionally warmer and fractionally cooler, mapped in exquisite detail by spacecraft built for the purpose, and those almost imperceptible ripples are among the most important features in all of science. They are the imprint of the slightly denser and slightly thinner regions of the infant universe, and the denser patches are the seeds from which everything later grew, the places where matter would gather over billions of years into the first stars and the first galaxies. The coldest, oldest, most uniform light in existence carries, written faintly across it, the blueprint of all the structure that came afterward. The temperature of empty space is not only a floor, it is a photograph of the universe in its first moments, still arriving. Which ought to settle the question the whole journey has been circling. If the emptiness itself rests at 2.7 degrees, and nothing can passively cool below the emptiness around it, then surely 2.7 Kelvin is as cold as the universe naturally gets. The floor is the floor, except that it is not. Somewhere out among the stars there is a place colder than empty space, a natural place, shaped by no hand, that has somehow driven itself below the temperature of the void it sits in, below the ancient glow that bathes everything, down past the floor that nothing is supposed to be able to cross. It should be impossible. And understanding how nature managed it is the strangest turn left in the story. The place is called the Boomerang Nebula, and it lies about 5,000 light-years away in the southern constellation of Centaurus. When astronomers measured its temperature, they found something that should not have been possible, about 1 Kelvin. 1 single degree above absolute zero, and more than a degree and a half below the temperature of empty space itself. The Boomerang Nebula is colder than the cosmic background that bathes the entire universe. It is the coldest natural place we have ever found, and it is so cold that it does not glow faintly against the ancient background light the way everything else does. It does the opposite. It is colder than that background, so it absorbs it, appearing as a cold shadow cast against the oldest light in the universe, one of the only known things in all of nature darker and colder than the afterglow of the Big Bang. We found this out, fittingly, by listening rather than looking. The nebula first appeared through ordinary telescopes as a faint, lopsided smudge of light. Its uneven, curved shape is what earned it the name. But its temperature was pinned down with radio telescopes, the instruments that read the long, cold wavelengths in which the very coldest things glow. Astronomers watched how the nebula's gas met the cosmic background light passing through it, and saw the gas not adding to that ancient glow, but subtracting from it, drinking in a portion of the light as it went by. Only something colder than the background could absorb it that way, and so the measurement gave up its impossible answer. Later, sharper images revealed the true shape behind the smudge. Not really a boomerang at all, but a vast symmetrical hourglass. Two great lobes of gas streaming away from the dying star at the center in opposite directions, the visible exhaust of the cosmic refrigerator caught in the middle of its work. This breaks the rule we had just established. Nothing, we said, can passively cool below the background bath, because the background keeps gently topping up anything that tries. And that is true, for anything cooling passively, just sitting and radiating. So the boomerang cannot have reached 1 Kelvin by sitting still. Something must be actively cooling it, working against the background, driving its temperature down below the floor. There has to be a refrigerator out there. And there is. The Boomerang Nebula is a dying star. A star much like the Sun, near the end of its life, has begun shedding its outer layers into space. But it is doing so with extraordinary violence, flinging its gas outward far faster than such stars usually manage, at something like 150 kilometers every second, perhaps 10 times the speed of an ordinary stellar outflow. And that furious, headlong expansion is the secret, because expanding a gas cools it. We have already seen a gentle version of this. High over the summer pole, rising air expanded into the thinning heights and chilled, making the coldest spot in the Earth's atmosphere. The same principle runs every refrigerator and every air conditioner on Earth. Take a compressed gas, let it expand rapidly, and it cools. Because in pushing outward, the gas spends its own energy and has less motion left. Force that expansion hard enough and fast enough, and you can drive a gas not just cooler, but colder than its surroundings, which is precisely what a fridge does, making a cold box inside a warm kitchen. The Boomerang Nebula is that same machine, built on the scale of a dying sun. Its outflowing gas is expanding so fast, into such enormous volumes, that it has chilled itself all the way down to a single degree above absolute zero, below the void, below the background, below the floor that nothing is supposed to cross. Sit with the reversal in that. We spent this whole journey learning that cold is stillness, that the deepest cold gathers where nothing moves, in calm air, in permanent shadow, in the isolated dark. And the coldest natural place in the universe is none of those things. It is not still. It is not isolated. It is a star tearing itself apart, hurling matter outward at 150 kilometers a second. The coldest natural spot we know was made not by stillness, but by violent motion, by an expansion so fast and so vast that it outran the warmth of the entire cosmos. Cold, at its most extreme in nature, turns out to be something a dying star can manufacture, briefly, by throwing itself into the dark. And briefly is the word. This sub-zero chill is a passing phase. As the expelled gas keeps spreading and thinning, the refrigeration will falter. The gas will slowly warm back up toward the background and settle, in the end, at the same 2.7 Kelvin as everything else. The Boomerang's record-breaking cold is a window only a few thousand years wide in the long death of a star, a brief moment when nature dips below its own floor before relaxing back to it. The coldest natural place in the universe is also one of its most fleeting, so nature's record stands at about 1 Kelvin, achieved by a dying star running as a refrigerator and lasting only an eye blink in cosmic time. It is a magnificent number. And it is still not the answer to the question this whole journey set out to settle, because 1 Kelvin is still a full degree above the bottom, still not the coldest place that exists. The coldest places that have ever existed anywhere in the universe are colder than the Boomerang Nebula. colder than the dying star, colder than the void, colder than any shadow or distance nature has ever contrived. They have been driven down past a single degree, past 1,000th of a degree, to within a hair of absolute zero itself. And they are not adrift among the stars. They are not in space at all. They are here, on this planet, in rooms we built, made by hand. The coldest places we have ever found are ones we created ourselves. To grasp how we did it, start with why it should have been impossible. Every ordinary way of cooling something works by moving its heat somewhere colder, the only direction heat ever moves by itself. But to cool a thing below the cosmic background, below 1 Kelvin, below the coldest natural place in the universe, there is no somewhere colder left to put the heat. The void itself is warmer than where you are trying to go. So the old method fails completely. And to reach the true bottom, physicists had to stop dumping heat into a colder place, and instead remove the motion from matter directly, to reach into a cloud of atoms and take away their movement itself, atom by atom, with nothing colder required at all. The first and strangest tool for this is light. We think of light as something that warms. Sunlight heats a wall. A laser can cut steel. And yet, used with enough precision, light can be made to cool. The trick rests on the fact that light carries a tiny push. Photons have momentum. When an atom absorbs one, it gets a small shove in the direction the light was traveling. Now tune a laser very carefully, and aim beams at a cloud of atoms from every direction, and arrange the tuning so that an atom only absorbs a photon when it is moving toward the beam, so that every photon an atom catches is one coming head-on, shoving against its motion. Whichever way an atom tries to move, it runs into light that pushes it back. The cloud sinks into what physicists call an optical molasses, every atom slowed by the gentle, relentless pressure of precisely aimed light. And since temperature is nothing but the motion of the atoms, draining away that motion is, exactly, cooling. Laser cooling alone can bring a cloud of atoms down to millionths of a degree above absolute zero, already far colder than the Boomerang Nebula, far colder than anything in the natural universe, achieved with nothing but carefully tuned beams of light. But millionths of a degree was only the beginning. To go further, physicists borrowed a trick from a hot cup of tea. Blow across the surface of the tea and it cools, because the fastest, most energetic molecules are the ones that escape as steam, carrying away more than their share of the heat and leaving the slower, cooler ones behind. The same idea works on a trapped cloud of ultra-cold atoms. Hold the atoms in a magnetic trap with a kind of lip around its edge, and let the fastest, hottest atoms spill over that lip and escape. What remains is colder than before. Lower the lip a little. Let the next fastest atoms escape, and the remainder is colder still. Skim off the hottest again and again, evaporative cooling, and the dwindling cloud that stays behind sinks down past the millionths into billionths of a degree above absolute zero. Nanokelvin, a cold 1 billion times deeper than the cosmic floor. And at that unimaginable cold in 1995, in a laboratory in Boulder, Colorado, the physicists Eric Cornell and Carl Wieman watched matter do something no one had ever seen. They had cooled a few thousand atoms of rubidium to less than 100 billionths of a degree above the bottom. And at that temperature, the atoms stopped behaving as separate things. Their motion was so nearly gone, their individual identities so blurred by the rules of the very small, that thousands of them collapsed together into a single shared state. No longer a crowd of atoms, but one unified quantum object, all of them occupying the same state at once, behaving as a single entity. It was a new form of matter, a Bose-Einstein condensate, predicted by Einstein and the physicist Satyendra Bose some 70 years earlier and never before seen, because nothing in the universe had ever been cold enough to make it. Within months, Wolfgang Ketterle at MIT had created one too, with sodium atoms. The achievement won a Nobel Prize, and it confirmed something staggering. By hand, in a sealed chamber, human beings had produced a cold deeper than the universe has ever managed on its own. This is where the long human thread of this story arrives. It began with cold as a feeling on the skin, a boundary marked by frozen water and aching fingers. It passed through the first glass thermometers, and the quiet realization that the falling line of a cooling gas must reach a bottom somewhere far below any cold that could be made. It ran through observers learning to read the temperature of unreachable worlds out of the light they emit, and through small crews enduring the dark at the bottom of the Earth. And it ends here, with physicists who learn to do what no star and no void can do, to remove motion from matter atom by atom until they reached a stillness deeper than anything in nature. We did not find the coldest place in the universe. We built it on a bench, and we can build it again whenever we choose. The coldest places that have ever existed are the ones we made, and yet, this is the thread that ties the whole journey shut, even here. Even with every tool we possess, we cannot reach the floor. The third law holds as firmly in the laboratory as it does everywhere else. The physicists reach billionths of a degree, then trillionths, halving and halving the distance to absolute zero, and the bottom stays exactly as far away as ever, untouchable, approached but never arrived at, with the faint, unfreezable shimmer of zero-point motion always remaining. They are pressing matter closer to the forbidden bottom than anything in all of existence has ever come. And the closer they press, the more clearly matter shows that the floor was never just a number. It was a doorway, because at these temperatures, with motion almost wholly stripped away, ordinary substances stop behaving like themselves entirely and begin doing things that have no equivalent anywhere in the warm world we live in. But before we open that door, there is a frontier still being pushed, colder records, stranger machines, and a chamber sent off the planet altogether to chase a cold that even the laboratory bench cannot quite reach. The records did not stop at billionths of a degree. They have been pushed steadily lower since, into trillionths, picokelvin, 1,000 times colder still than the first condensates. In specialized experiments, physicists have cooled small samples to within a few trillionths of a degree of absolute zero, the lowest temperatures ever recorded anywhere by an almost absurd margin. These are colder than the Boomerang Nebula by a factor of 1 trillion, colder than the cosmic background by 1 trillion, so far below anything the natural universe produces that the comparison stops meaning very much. They are simply the coldest things that have ever existed, and they exist only because we make them. But the very coldest temperatures are reached only in the tiniest scraps of matter, a faint cloud of a few thousand atoms, a speck too small to see, chilled for a fraction of a second. There is a second frontier that runs the other way, not the lowest temperature, but the largest thing ever held cold. And the champion there sits deep beneath a mountain in Italy. In the Gran Sasso laboratory, buried under more than a kilometer of rock to shield it from the noise of the world above, physicists built an experiment called Cuore, and to make it work, they had to cool not a wisp of atoms, but a massive array of crystals, close to a ton of material, filling roughly a cubic meter, down to about 10,000ths of a degree above absolute zero, and hold it there steadily for months and years on end. Nothing else in the known universe combines that much mass with that little warmth. Cuore has been called, with good reason, the coldest cubic meter in the cosmos, the largest volume ever brought so close to the floor and kept there. It is chilled so deeply because it is listening for one of the rarest events in physics, a whisper of nuclear decay so faint that the entire apparatus must be held in near-perfect stillness for the signal to stand out from the dark. To hear something that quiet, you must first make a place that cold. An entire room's worth of detector, held 1/100th of a degree above the bottom, beneath a mountain, in the dark, for years. Between them, these two frontiers, the coldest tiny speck and the coldest large volume, have left every natural cold in the universe far behind. And then the chase did something stranger still. It left the planet. The problem with reaching the very lowest temperatures on Earth is gravity. To coax atoms toward absolute zero, you want to hold them in the gentlest possible trap and watch them for as long as you can. But the gentler the trap, the less it can resist the pull of the Earth. And the moment you loosen your grip, gravity drags the delicate cold cloud downward, and it falls away within a fraction of a second. The experiment ends before it has properly begun. The only way to truly let go of the atoms is to remove gravity's pull altogether, and the way to do that is to fall. So in 2018, NASA installed a device called the Cold Atom Laboratory aboard the International Space Station, a sealed box about the size of a small refrigerator that makes Bose-Einstein condensates in orbit. Because the station is in continual freefall around the Earth, everything inside it is effectively weightless, and inside that box, the cold clouds of atoms simply float, freed from the gravity that would yank them to the floor of any laboratory on the ground. Released into the gentlest of traps, with nothing pulling them down, they can be held and studied far longer than is possible on Earth, drifting into colder and more fragile states than gravity below would ever permit. At intervals, as it circles overhead, that small box becomes the coldest known place in the entire solar system, colder than the shadowed craters of the moon, colder than the distant ice of Triton, colder than the dark between the planets. We have begun building the coldest places in the universe not only on our world, but above it, sending the chase into orbit precisely because the Earth's own gravity stands in the way of going lower. And through every one of these frontiers, the picokelvin speck, the coldest cubic meter, the condensate adrift in orbit, the oldest rule holds without a crack, trillionths of a degree above absolute zero, and the floor is not one step nearer than it was for the first crude thermometer. It remains exactly where it has always been, approached forever, never touched, the faint shimmer of zero-point motion still refusing to be stilled. Which raises the only question that really matters about all this effort. Why chase a cold 1 trillion times deeper than anything in nature, build refrigerators beneath mountains, send chilled atoms into orbit to gain another trillionth of a degree that brings you no closer to a floor you already know you can never reach? The answer is that the temperature was never the point. The point is the door it opens, what matter itself begins to do when nearly all of its motion has been taken away, and the strange quiet behavior that emerges only at the edge of absolute stillness. What matter does near absolute zero begins with a substance that refuses to behave like any other, helium. Cool almost anything far enough and it freezes solid, its atoms locking into place. Helium never does. At ordinary pressure, it stays liquid all the way down to the bottom of the temperature scale, the only substance in nature that will not freeze no matter how cold it gets. And the reason is the faint shimmer we met long ago, the zero-point motion that can never be removed. Helium's atoms are so light and so weakly bound that even that last unfreezable tremor is enough to keep them sliding past one another forever. The floor's permanent quiver, invisible everywhere else, here keeps a liquid down to the edge of absolute zero. And then, a little above 2 Kelvin, that cold liquid does something extraordinary. It becomes a superfluid, a liquid with no viscosity whatsoever, no internal friction at all. And once that happens, it stops obeying the rules every other liquid lives by. Set an ordinary liquid swirling, and it slows and stops, its motion drained away by friction. Set a superfluid swirling, and it circulates on and on, essentially forever, because there is nothing to slow it. Its flow never fades. Pour it into an open cup, and it will not stay there. A superfluid creeps up the inner wall in a film only atoms thick, flows over the rim, and drains down the outside, emptying its own container by climbing out of it, because nothing resists its motion, and it will follow any path, even upward and over a wall, to find a lower place. It seeps through cracks and pores far too fine for any normal liquid to pass, slipping through gaps that would stop water cold, because it has no friction to hold it back. Warm one spot of it gently, and it leaps upward in a continuous fountain that can run for as long as the warmth is applied. It is recognizably a liquid, and it does things no liquid in the warm world could ever do. All because, at that temperature, the friction that governs every ordinary flow has simply ceased to exist. There is a stranger detail still. When superfluid helium flows, it can do so in two ways at once, as though it were two liquids sharing the same space. One part behaving like an ordinary fluid, the other utterly frictionless, slipping through and past the first. Stir it, and the frictionless part organizes its motion into thin, permanent whirlpools that, once formed, can never wind down, each one spinning in a fixed amount that never blurs or fades. These are not the swirls of ordinary water, which smear and slow and vanish. They are precise and indestructible, everyone carrying exactly the same fixed quantity of spin, lasting for as long as the helium stays cold. Eddies that, in principle, could outlast the people watching them, turning quietly in a sealed flask while everything around them changes. It is one of the first hints of what is really going on down here. That the cold is not merely slowing the liquid, but reorganizing it into something that obeys different and far more rigid rules than any warm fluid ever could. The same impossible thing happens to electricity. An electric current in an ordinary wire fades because the wire resists it, and that resistance turns the current's energy into heat. It is why wires warm and why no current runs forever. But cool certain materials toward absolute zero, and their resistance does not merely fall. It vanishes completely to exactly nothing. The material becomes a superconductor, and a current set flowing in a loop of it will circulate for years on end, with no battery and no source of any kind, losing not a trace of its energy, because there is nothing left to resist it. Flow without friction, current without resistance. The same surrender of the everyday rules, showing up once in the motion of a liquid, and once in the motion of electricity. It was discovered more than a century ago, in 1911, by Heike Kamerlingh-Onnes, the same physicist whose laboratory had just become the first in the world able to make liquid helium, and so the first able to reach these temperatures at all. He cooled a thread of mercury toward the bottom of the scale, and watched its electrical resistance drop away to nothing, and could scarcely believe it. He was, in the truest sense, another of the cold chasers in our long thread, someone who reached a temperature no one had touched before, and found that matter there had stopped being what he expected. And superconductors do one more thing that looks, plainly, like magic. A superconductor pushes magnetic fields out of itself, and the result is that a magnet brought near one will hover above it, floating motionless in the air, held up by nothing visible at all. Frictionless, effortless, losing no energy, able to hang there as long as the cold is maintained. It is one of the few places in physics where the strangeness of the very cold becomes something you can simply watch with your eyes. A small magnet, suspended in midair over a chilled disk, going nowhere, forever. Stand back and feel how strange all of this is. The warm world we live in runs on friction and resistance and loss. Everything that moves slows down. Every current fades. Every motion has a cost, and every flow runs out. And we take that so completely for granted that we never think to question it. It seems like the deepest law there is. And then, at the edge of absolute zero, with nearly all the motion stripped from matter, that law quietly switches off. Flow becomes endless. Current becomes eternal. Liquids climb out of cups and magnets hang in the air. Matter begins doing things that are not merely difficult, but, by every standard of ordinary experience, impossible, and it does them not in spite of the terrible cold, but because of it. The obvious question is why. Why should taking away the heat unlock frictionless flow, currents that never die, a liquid that creeps up walls? These do not look like one phenomenon. They look like a handful of unrelated tricks, but they are not unrelated at all. They are the same thing seen from different angles, a single profound change in what matter fundamentally is once it is brought close enough to stillness. And understanding that one change is the deepest thing the cold has to show us. The reason all those impossible behaviors are really one behavior comes down to what heat has been hiding from us the whole time. At ordinary temperatures, matter is chaos. The atoms in anything warm are a frantic, disordered crowd, jostling, vibrating, colliding billions of times a second, every one of them careering off on its own. And in that thermal bedlam, the deepest truth about those particles stays completely hidden. Because the rules that really govern matter are not the rules of little solid balls bouncing around. They are the rules of the quantum world, where every particle is also a wave, spread out and uncertain, with a wavelength all its own. That quantum nature is always there, underneath everything, in the wall and the air and your own hand. But at normal temperatures, the heat is simply too loud. The motion is so violent and so disordered that each particle's delicate wave is scrambled down to something fantastically tiny, far smaller than the atom itself, and the quantum world stays sealed away at scales we can never see. The heat drowns it out. Cooling is how you turn the noise down. As matter cools and its particles slow, something quiet and profound happens to those hidden waves. They grow. The slower a particle moves, the longer its quantum wave stretches out. Cool a little, and the waves lengthen a little. Cool toward the very bottom, and the waves swell until they are no longer tiny at all, until each atom's wave reaches as far as the distance to its neighbors, and then farther. And the private, separate waves of the individual atoms begin to overlap. And at the bottom, they merge. In a Bose-Einstein condensate, the waves of all the atoms have stretched and overlapped so completely that they fuse into a single wave. The atoms stop being separate things. They fall into one shared state, all of them doing precisely the same thing at once, a single quantum entity spread across the whole sample, large enough to hold in a trap and photograph. Cold added nothing to make this happen. It only took away the thermal roar that had been hiding it, until the quantum nature of matter, normally locked away in the invisibly small, swelled up into something the size of a visible cloud. That single change explains every impossible trick at once. A superfluid flows without friction, because friction is what happens when individual atoms get knocked off course one at a time. And in a single shared quantum state, there are no separate atoms to knock about. To slow the flow, you would have to disturb the entire unified state in one go. And the gentle obstacles in its path simply cannot deliver a jolt that large, so the superfluid slides past all of them as one, untouched. A superconductor carries its current forever for exactly the same reason. The electrons have paired up and fallen into a single shared quantum state, moving as one coherent whole, with no individual electrons left for the material to scatter, so the current meets nothing to resist it and never dies. The liquid creeping up the wall, the current that runs for years, the magnet hovering motionless in the air. They are not separate marvels at all. They are one fact, seen from different sides. Matter has stopped being a crowd of independent particles and become a single quantum thing, behaving with a unity that, anywhere else in the universe, belongs only to the unimaginably small. This is what the cold truly reveals, and it is far stranger and larger than any temperature record. The quantum world, the deepest layer of reality, the rules underneath everything, ordinarily sealed away at scales no eye and no instrument can directly perceive, is dragged up into the open by the cold. At the edge of absolute zero, with the thermal noise stripped almost entirely away, the bizarre behavior that normally belongs only to single particles becomes the behavior of something you can see in a flask and watch float in the air. Cold is the one condition in the universe under which reality's most hidden layer rises to a size we can hold. The floor was never just a number to approach. It was a doorway, and what lies on the other side of it is not a colder place, but a different and truer face of matter itself. That is the real answer to the question we left hanging: why anyone goes to such lengths, chilling matter beneath mountains and in orbit, for the sake of one more vanishing fraction of a degree. Not for the record. To hold that door open a little wider. To make the quantum world large and slow and visible, where it can be studied and understood and built upon, and nearly every technology that reaches into the quantum, from the superconducting magnets inside medical scanners to the most precise clocks and sensors ever made to the machines now being coaxed toward quantum computing, is a child of this near absolute cold. The coldest places we have ever made are the places where the universe briefly shows us what it is made of underneath. And there is a final turn in that, waiting at the end of the journey. We set out treating cold as absence, as ending, as emptiness, as the place where things run down and stop. We have found it to be very nearly the opposite. The condition that preserves the most, that reveals the most, that the universe overwhelmingly chooses. Warmth is the brief local exception. Cold is the rule, the floor, the vast quiet background against which everything else is a passing flicker, and it is more than the universe's present state. It is, slowly and certainly, the universe's destination. The universe is cooling, and it has been from the beginning. We have already watched it happen across 13.8 billion years. The searing glow of the early cosmos, once thousands of degrees, stretched by the expansion of space down to the faint 2.7 Kelvin of the background that now fills the sky. That cooling has not stopped. As space goes on expanding, the background goes on falling. Toward 1 Kelvin, toward a tenth, toward 100th. Drifting ever nearer to the floor it can approach forever and never touch. The temperature of the universe is a number that has only ever gone one way, and it will keep going that way for as long as there is a universe to have a temperature. Follow that descent far enough into the future, and the consequences are staggering and strangely quiet. The stars are not eternal. Each one burns through its fuel and dies, and while new stars are still being born today, the gas to make them is finite and steadily being spent. The rate of star birth across the cosmos has already passed its peak and has been declining for billions of years. There will come a time, far off, trillions of years from now, when the gas runs too thin, the last stars form and burn and gutter out, and no new ones rise to replace them. The lights go out, not all at once, but one by one, until the sky holds only embers. And then the long cold begins in earnest. What remains after the stars, the slowly cooling cinders of dead suns, the dark drifting matter, the black holes, radiates away its last warmth into an ever emptier, ever colder dark. Over spans of time that make the present age of the universe look like an instant, even the black holes will evaporate, and the cosmos will settle toward a state of near uniform, near absolute cold. Matter spread impossibly thin, motion almost entirely run down, everything hovering just above the floor that nothing can cross. It is sometimes called the heat death of the universe, but the name is misleading. It is not a death by heat. It is the slow and final triumph of the cold, the same cold we have spent this whole journey chasing, arriving everywhere at once for good, which casts everything we have seen in a different and larger light. The deep cold we traveled to find, the stillness of the Antarctic plateau, the frozen dark of a lunar crater, the 2.7 Kelvin of the empty void, even the strange sub-zero chill of a dying star was never a set of exotic exceptions scattered through a warm and ordinary cosmos. It was a preview. We were visiting, ahead of time, the condition toward which the entire universe is drifting. The coldest places are not strange corners of a warm universe. They are the early arrivals at its final state, the parts of the cosmos that have already reached, or nearly reached, where all of it is slowly going. It is warmth that is the anomaly. Warmth is this brief, bright, improbable era, the age of burning stars and lit worlds, the narrow window in the universe's history when there is still enough heat and structure and motion for planets to gather, and oceans to pool, and life to stir on at least one small world and look up. By the measure of the cold eternity ahead, this entire luminous chapter, every star that has ever shone, and everyone that ever will, is a short-lived flare against a darkness that came before it and will remain long after. We do not live in the universe's natural state. We live in its fleeting exception, the morning before the long cold settles in. And that is not cause for grief. It is the most extraordinary good fortune imaginable. We exist in the one brief window when the universe is still warm enough and lit enough to be understood, when there are still stars to study, still heat to measure, still observers who can arise and look around while the lights are on. The cold future is unimaginably long, and the warm moment is now, and we are inside it. We are, as far as we know, the universe's brief chance to understand itself before the dark. And consider what we did with that chance. A species on a single small world, living in this narrow, warm window, learned to read the cold, to feel it first only on the skin, then to put a number on it, then to extend that number down to a floor no one could ever reach. We learned to measure the temperature of worlds we will never touch out of the faint light they cannot help but give off. We sent a probe falling for 9 years across the solar system to read the frost on a distant world and cruise into the long polar dark to keep watch at the bottom of our own. And then we did something the universe itself, in all its billions of years and across all its vast cold reaches, had never managed. We reached past the coldest place nature has ever made. In sealed chambers and beneath mountains and in a small box circling overhead, we built a stillness deeper than the void, deeper than the dying star, colder than the background glow of creation itself. And in that impossible cold, we found not emptiness, but a doorway. And through it, for the first time, the deepest face of what everything is made of. That is the strange gift the cold turned out to hold. We came to it fearing an ending, a running down, a going out, the place where things stop. We leave it having found the reverse, the state that holds the universe together longest, that shows us the most about what we are made of, and that everything is quietly returning to. The cold was never the enemy of the story. It was the floor of the room the whole universe has always been standing in, the vast, patient quiet beneath every fire, and the warmth we cherish, including our own, is a brief light kindled in that great cold hall. We are the small, warm thing that learned to look down at the floor and to build, with our own hands, a colder fire than the dark around us. And by its strange light, we saw what holds the universe up. If you enjoyed this journey to the coldest places in the universe, a like or a subscribe helps us continue making them. The cold is where everything is going, and it is also where we have already gone, further in a sealed room on a warm and improbable world than the universe has ever gone on its own. The floor remains untouched, as it always will. But we have stood closer to it than the void, closer than the dying stars, close enough to see by its light. The universe still has plenty left to reveal, and we will be following it as it does.